Now, having looked at the individual terms in the joint probability distribution, which is the prior distribution, the transition probabilities, as well as the emission probabilities for the hidden Markov model, the next thing that we are going to look at is to find the maximum likelihood for the hidden Markov model. The likelihood function is obtained from the joint distribution by marginalizing over the latent random variables, as what we have seen in the previous lecture. So what we are after over here would be the probability distribution of all the observed random variable conditioned upon the unknown parameters, and this is equals to the marginalization over all the latent random variables all on the joint probability distribution of the observed random variable and the latent random variables conditioned upon the unknown random variables. And what's interesting here is that we cannot treat each one of the sum over Zn independently, because the joint probability distribution does not factorize over Z1 all the way to Zn over here, in comparison to what we have seen in the previous lecture on the Gaussian mixture model, or the mixture model in general, where each one of the latent random variable is independent of the others, given by this particular plated notation over here. Hence, in this case over here, we can actually write this marginalization into the marginalization of Zn xn condition upon xn Zn condition upon theta, and the product term of the all the n observations over here. But in this particular case, since all the latent random variables, they are dependent on one another, so here we can no longer decouple this or factorize this into a product term over the n random variable. So over the marginalization of each individual term of Zm, and performing the function or performing the sums over all the n random variable would result in the exponential complexity. What this means is that in this case here, we would have to perform the marginalization over all the n z's, the latent random variable that we have, where each one of it is going to take k states, and altogether we would have a complexity of k to the power of n complexity in just performing this marginalization alone. Moreover, a direct maximization here will lead to no closed form solutions. This is the same as what we have seen in the previous case, because in this case here, if we were to take a log likelihood and directly argmax this over theta, this would be equivalent to taking the argmax over theta on the log of the marginalization of all z's over here. And we have seen in the previous lecture that this log term cannot be pushed into the summation term here. Hence, all the unknown random variables, they are all going to be coupled together, and it will lead to a no closed form solution here. And in this case of the HNM, in addition to this no closed form solution, we also saw earlier that this summation, the marginalization over Z, cannot be decoupled into the product of n terms. It has to be all done in at one go. So we'll turn to the expectation maximization algorithm to find an efficient framework to maximize the log likelihood function in the HNM model. So we'll follow the same step as what we have seen in the previous lecture, that the EM algorithm alternates between the expectation and the maximization step. And it all starts with an initialization of the model parameter, which we denote as theta O. So in this case here, theta O will be theta would be our pi, which is the categorical distribution of the prior term, as well as the transition matrix denoted by A, and phi, which is our emission probability. So this is different from the mixture model or the Gaussian mixture model that we have seen in the previous lecture, but the concept of the EM remains the same. So in the expectation step, or otherwise known as the E step, we take these parameter values and find the posterior distribution of the latent random variable. So this step here remains the same, and then we will make use of the posterior distribution of the latent random variable pz conditional upon x and theta o to evaluate the expectation of the log complete data likelihood as defined by this term over here. So this guy over here, this expression over here, is exactly the same as what we have seen in the previous lecture, but there is a very subtle yet important difference over here, because now the z's over here, all the latent random variables, can no longer be decoupled. So z1 all the way to zn, they are no longer decoupled. This means that we can no longer write this into a product term over n over here, and hence this z here would have to be coupled together in the first order Markov chain. That means that in addition to the independent posterior of p of z n conditional upon x theta o, we would have an additional term of p of zn and zn minus 1 conditional upon x and theta o over here. Well, it's all because of this particular coupling of the consecutive latent random variable in our hidden Markov model. Hence, let us denote the marginal posterior distribution of a latent random variable zn as gamma zn. This is equivalent to our responsibility function, which we have seen in the previous lecture here, and this would be defined as the posterior distribution of zn conditional upon x and theta o. Now, as I've mentioned earlier, that due to the coupling of the latent random variable, there's an additional term that we need to define, which we call psi of zn minus 1 and zn. This is essentially equivalent to the posterior joint distribution of zn minus 1 zn conditional upon x and theta o. And this term over here, it arose all because of the link between the consecutive latent random variables of zn minus 1 as well as zn. Now, what this means is that for each one of these gamma zn, it will consist of k non-negative numbers that sums to unity, since this is essentially equivalent to the posterior distribution of zn conditional upon x and theta o, where zn over here is taking 1 out of k state. So 1 out of k states. This means that I would have k probability values that describe every one of these states that zn can take, and hence I would have k non-negative values that sums to unity, where each one of the value is between 0 and 1. Similarly, we can also store psi of zn minus 1 equals to zn using a k by k non-negative number that sums to unity. So essentially, this simply means the joint probability distribution of zn minus 1 and zn, and which is defined in the previous slide, where I have the joint probability distribution of zn minus 1, zn condition upon x and theta o over here. So here, in this case, it would be just simply a k by k table or a k by k matrix that represents the joint probability distribution. And of course, in order to make this a valid joint probability distribution, the total probability must sum out to unity, which means that it must sum out to 1. So we shall make use of this shorthand over here of gamma znk to denote the conditional probability of znk equals to 1. This means that I'm going to denote this probability that zn taking a state of k conditioned upon the observed random variable of x and theta o over here, and I'm going to shorthand this using this notation of znk, as well as I'm going to use similar notation for psi over here, where this simply denotes the probability that zn minus 1 is going to take a state of j and zn is going to take a state of k conditioned upon all my observed random variables, as well as the o parameters denoted by theta o over here. Furthermore, we'll define the expectation of a binary random variable is just the probability that it takes the value of 1. So we can see that this expectation over here, which is equivalent to expectation of Znk over here, is equivalent to the marginalization over Zn on the posterior distribution. So this guy over here is equivalent to the posterior distribution of Zn conditioned upon x and theta O multiplied by this random variable of Znk. This means that I'm going to look at Znk or Zn taking a state of k over here, and I'm going to marginalize this over all the possible states of Zn, which actually evaluates to, so this term over here, the summation term over here, it evaluates to Zn equals to 1 conditional upon x theta O multiplied by Zn taking a state of k over here, and then plus all the way until Zn taking a state of k conditional upon x theta O and multiplied by Zn taking a state of k plus all the way until Zn equals to capital K x theta O and Zn taking a state of k over here. And in this case here, the summation, all these summations over here, only one particular term where Zn equals to k would be 1. All the rest here would be 0, since we are summing over all the possible states of Zn, and hence this particular term here remains. And since Zn equals to k here would be 1 over here, while all the rest are 0, so hence we will be remaining this particular term here where it's equivalent to Zn taking a state of k conditional upon x and theta O over here. Hence this would be equivalent to gamma Znk, which is our shorthand earlier, and hence the expectation of Znk, which is given by this definition over here, would be equivalent to gamma of Znk. We can also evaluate the same thing for the side term over here, where over Zn minus 1 and Zn, where Zn taking a state of k and Zn minus 1 taking a state of j. So we'll take the expectation over these two random variables over here, where Zn minus 1 taking a state of j and Zn taking a state of k over the posterior distribution, this guy over here, the joint posterior distribution of Zn minus 1 and Zn conditioned upon x and theta O over here. So this is this guy over here, and then multiply by these two terms, and marginalizing over Zn minus 1 and Zn, we can also see that since these two terms are only 1 when Zn minus 1 taking a state of j and Zn taking a state of k, hence we are remaining this term over here where Zn minus 1 is going to take a state of j and Zn is going to take a state of k, which is going to be rewritten as psi of Zn minus 1 j and Zn k over here. So now, having defined all the terms, we are going to put everything together into the expectation step to define the function of q, where we can see that it's a marginalization over all the latent random variable on the posterior over the log complete data likelihood of x and z over here, where x and z is actually given by this joint probability distribution that we have defined earlier, that is made up of the prior term, the transition probabilities, as well as our emission probabilities over here, and directly plugging in all the terms that we have defined, where the prior term is given by the categorical distribution, the transition term is given by the A matrix over here, and the emission probability is given by this product terms over here, this expression over here. So plugging this into the Q term, we will get this particular complicated expression over here. Now we can push this marginalization over Z on the posterior of Z into the individual summation terms over here, and we can see that this evaluates to this particular equation over here, where let's look at one particular term over here, the first term, where we push this summation over z into this term over here. We can see that since it's an expectation over z on z1k over the posterior distribution of z, and this ends out to be gamma z1 of k. Since this is defined over 1 of and k here, we'll end up with this particular term in accordance to what we have defined earlier on in the in this particular slide over here on gamma nk and psi znj and znk. So we can see that this term starts to appear, and we can replace the summation over z with this simply this term over here, and this would be the expectation over the z1k, as well as we can also see that if we push this particular term into here, we can see that there are two terms over here which we can evaluate into this psi zn minus 1j and znk, which is equivalent to the expectation term that we have defined 2 slides ago. Similarly, the third term over here, we can push this summation over z into the third term over here. We can also see that this resulted, since there's a zmk over here, it resulted into this particular term here. So in this case, we will take a maximization over this particular expression on all the respective unknown parameters. What remains here is to how to effectively compute this gamma psi terms in this Q function over here. We'll defer this to later slides. We'll first talk about the maximization before we talk about the how to evaluate these two terms here effectively using the forward and backward algorithm. So in the expectation step, we need to evaluate these terms first, followed by a maximization step where we maximize over all the unknown variables or the unknown parameters, keeping gamma and psi in the expectation step fixed. So in the maximization step, or otherwise known as M step, we'll simply maximize the Q function with respect to all the parameters in theta, which consists of the categorical distribution pi of the prior term and the transition matrix A, as well as the emission probabilities of psi over here, in which we treat the gamma and psi as a constant term. So this is similar to the responsibility function as what we have seen in the mixture model in the previous lecture. So maximization of the pi term and A is easily achieved using the Lagrange multiplier. So this is because the sum of all the pi must add up to 1, and the sum of all the rows of this guy A over here must also add up to 1. So we'll end up with these two expressions for pi k as well as the individual term of aij or ajk within the transition matrix. And it's also very important to note that the EM algorithm must be initialized by choosing the starting values of pi and a with the summation constraint, because if we choose it to the initialization to be violating these summation constraints, then the following steps of the EM algorithms will be computing the wrong pi and a that are violating the summation constraints. And another important thing to note is that we cannot initialize pi and a to be 0. Otherwise, it will remain 0 in all the subsequent EM steps. And typically, we will set the random values for this parameter just subjected to the constraints of the summation as well as the non-negativity constraint. Now, assuming that the emission probability distribution is given by a Gaussian distribution where our random variable of x over here is a continuous random variable, we can write this emission probability as equals to a normal distribution which is parameterized by mu k and sigma k. this assuming that Zn over here is taking a state of k. Hence, we are looking at the k set of unknown parameter mu k and sigma k in phi k over here, and we'll maximize this q function with respect to this unknown parameter of phi k, which is parameterized by mu k and sigma k, since we assume that x is following a continuous normal distribution. And by doing this, we'll get mu k given by this expression over here, and sigma k given by this particular equation over here. For a discrete multimodal random variable of x, we'll denote x as a d-dimensional random variable, where each dimension here, where this is actually a one-hot vector, a d-dimensional one-hot vector that represents x taking a certain state. Hence, x over here would follow a categorical distribution, which is given by this equation over here, where mu is our parameter, unknown parameter for the categorical distribution. And if xi over here, this means that the d-dimension, the ith dimension of x over here equals to 1. This means that x is taking a particular state, the ith state. Then we will look at the probability that is given by mu I k over here, conditioned upon that z is taking a state of k. And by doing this corresponding maximization step over the unknown parameter of mu over here, we'll get this particular equation for mu that parameterizes the categorical distribution of the random variable of x. Now we'll look at the forward-backward algorithm to compute the gamma and psi function over Zn and Zn minus 1 respectively. We'll look at how this forward-backward algorithm can be used to compute these two terms efficiently. It's also known as the bulk-val algorithm, and there are many variants of this algorithm. We shall focus on the most widely used of these algorithms, known as the alpha-beta algorithm. We'll also see why is it called the alpha-beta algorithm. We'll make use of some of the conditional independence properties that can be read off directly from the hidden Markov model, as shown in this diagram over here, to help us derive the forward-backward algorithm, or the alpha-beta algorithm. I'll leave it to you to look through these conditional independence properties, but I will explain them as I derive the alpha-beta algorithm in the later slides. So let's first look at the evaluation of the gamma function over Zn taking a state of k. We are interested in finding the posterior distribution of Zn conditioned upon x1 to xn, where all these are actually our observations or observed random variables. So gamma n over here is defined to be equals to the posterior of Zn conditioned upon x, where we can apply the Bayes rule to flip this guy around into the likelihood function multiplied by the prior of z and divided by the normalizer constant over here. And the next step that we are going to apply would be the conditional independence of where condition upon Zn. This means that we are conditioning it upon Zn over here, where we observe Zn. We can see that once we have observed Zn over here, Zn minus 1 and Zn plus 1 over here. So once we have observed Zn, all the x that are preceding Zn, it will become de-separated from xn and xn plus 1 on all the way to x of capital N over here. So all the way from xn, it will be all this bunch of random variable here. Since we observe this, it will be decoupled from xn, as well as all the other bunch of random variables that from xn plus 1 all the way to x capital N over here. Hence, we can rewrite this joint probability distribution, or this conditional probability distribution, into x1 to xn conditioned upon Zn, multiplied by the probability distribution of x1 n plus 1 to xn conditional upon zn multiplied by p of zn, since we have observed zn. This means that everything else becomes decoupled. All the observations here becomes decoupled into two groups over here, and zn here is what we have seen in the previous step. The next thing that we do here is that we rewrite the conditional probability here using the product rule, which is given by this term over here, where the prior distribution of zn cancels out each other, and then what will remain with will be these two terms over here, which we can rewrite into the terms of alpha of zn, which represents the joint distribution of x1 to xn and zn, multiplied by beta zn, where beta zn is defined as the conditional probability of xn plus 1 to x capital N conditioned upon zn. And this would be divided by the normalizer, which is the joint probability of all the observed random variable. So in this case here, this guy here is actually a scalar number. We can evaluate this to be a scalar number. It's just one division over the scalar number. Now we'll proceed on to look at how to compute alpha and beta over here. So we have defined these two terms of alpha beta, which is the joint probability as well as the conditional probability terms over here, and alpha and beta can be both represented respectively by k numbers, one for each possible setting of one of k coding of the binary vector. So we'll look at how to compute this k by 1 and k by 1 vector of alpha and beta over here, since both of them are dependent on only one random variable, which is zn, in the probability distributions here. Now the alpha term over zn can be computed as this given by this expression over here, which we will call the forward recursion. This the reason of forward recursion is because alpha of zn can be computed from recursively computing the previous term of alpha of zn minus 1. So we can start from z1 to compute alpha z1 to compute alpha z2, and then recursively all the way until we can compute alpha zn from the term of alpha zn minus 1. Hence it's called a forward recursion, because we always compute the higher order of the z from a consecutive lower order of the z over here. And let's look at the proof on that this particular forward recursion expression here is true, where alpha zn will start off from the definition of alpha zn, which we have seen earlier to be the joint probability distribution of x1 all the way to xn and zn over here, and this is going to be equal to by making use of the product rule, we can rewrite this as the conditional probability of x1 to xn conditional upon zn multiplied by zn. Then the next thing that we can do here would be, since this term is conditional upon zn over here, we can make use of the conditional independence. So zn, if we observe this term here, we can observe that all these terms here, they are all going to be conditionally independent of this xn over here. Hence we can rewrite this conditional probability into these two product terms over xn and x1 all the way to xn minus 1 over here. Then the next thing to do would be to make use of the product rule to merge these two terms together into the joint probabilities of x1 to xn minus 1 and zn. Then we are going to introduce use a marginalization trick to introduce this additional random variable of zn minus 1 into our joint probability distribution here. The next thing that we will do will be to make use of the product rule to make the whole probability distribution condition upon zn minus 1, which will end up to be this expression over here. Then the next thing that we can do would be to make use of the conditional independence of zn minus 1. So in this case here, we can see that if we observe zn minus 1 over here, then all these terms here, they are all going to be conditionally independent of this Zn over here. Hence, we can rewrite this into a factor of these two terms, conditioned upon Zn minus 1. And finally, we can make use of the product term to get rid of this condition term and this prior term over here, to merge it together, these two terms over here, to merge it together into the joint probability distribution of x1 all the way to xn minus 1 and Zn minus 1. Which we can identify that this particular joint probability distribution here is actually equals to alpha Zn minus 1. Hence, we have proven that the forward recursion, or this alpha Zn, can be recursively computed from alpha Zn minus 1. So let's look at the actual computation of the forward recursion of the alpha term over here. So we can see that this particular term over here, since alpha Zn is a k multiplied by 1, k by 1 vector, which means that we have k entries in these alpha terms over here. And it's a marginalization over Zn minus 1. This means that this marginalization will contain k particular summation terms over here. And we can rewrite, which means that we can rewrite this term. Let's say, suppose that we are looking at alpha Zn equals to the state of 1. This is actually equals to p of xn, where xn is the observed random variable which stays fixed, conditioned upon Zn equals to 1, and marginalization over Zn minus 1. What this means is that we are looking at alpha Zn minus 1 equals to 1 multiplied by Zn equals to 1, conditioned upon Zn minus 1 equals to 1, plus alpha of Zn minus 1 equals to 2 multiplied by Zn equals to 1, conditioned upon Zn minus 1 equals to 2, plus all the way until Zn minus 1 equals to k, multiplied by Pzn equals to 1, conditioned upon Zn minus 1 equals to k. And this would be the evaluation term for the first entry of alpha. And we can see that suppose that if k over here equals to 3, then this guy over here, this curly bracket, all the terms in the curly bracket, would be a summation of 3 individual terms, which we can see that it corresponds to this particular trellis diagram over here. So in this case, we are computing alpha Zn equals to 1, which is denoted by this alpha Zn comma 1 over here, this particular term over here. And what's interesting over here is that what we are doing here is that we have 3 terms, 3 summation terms within this curly bracket, and that would correspond to alpha Zn equals to 1, Zn minus 1 equals to 1, which is this term over here. And we are going to multiply this with A11, which is given by this transition probability where Zn equals to 1, Zn minus 1 is also equals to 1. So what this means is that I'm going to take this multiplied by this term over here that is going into my Zn equals to 1 state over here, because I'm computing this alpha over here. And then the second term that I'm going to add up, the additional term, I'm going to take this term multiplied by this term, and then I'm going to add it up with this term multiplied by this term, which is equivalent to alpha Zn minus 1 equals to 2 multiplied by A21 over here. Then finally, since there are only 3 states over here, I'm going to take alpha Zn minus 1 equals to 3 multiplied by A31 over here, and these are all going to be summed out and go into alpha Zn equals to 1 over here. And finally, we are going to multiply all these sum of product terms with the emission probability of xn conditional upon Zn1, which is given by this term over here. We'll do this for alpha Zn equals to 2, where we'll compute the sum of product terms multiplied by the observations or the emission probability where n equals to 2 over here. Then we can do the same for alpha Zn3 over here by taking the sum of product term multiplied by the emission probability of xn Zn3 3. So as a result, we can see that the each step of the forward recursion has a computation cost of k square, because we are going to take all the product term, sum of the product term, which is over this k by k A matrix over here, and hence there's a overall computation or cost of k square over one recursive step. So altogether, for the forward recursion, you will incur n k square computational steps over the n number of random variables. So this slide is what I have mentioned earlier on the computational step, and one question remains is that how do we initialize this alpha value for alpha z1, the first random variable over here. We can see that alpha z1 is essentially equivalent to the joint probability distribution of x1 and z1. Hence, we only need to look at these two random variables over here in the graphical model, which obviously evaluates to this particular joint probability distribution, or the factorized expression over here, which can be given by the this term over here. This is similar to our mixture model that we have seen earlier in the previous lecture. And since pi and phi, which is our unknown parameter here, are actually initialized by theta O, which is already a known value over here, we can evaluate this term, this particular probability, the joint probability of x1 and z1 completely. And hence, as mentioned earlier, the total complexity for the whole chain is actually k square multiplied by n number of random variables. We'll now look at the backward recursion, which will enable us to compute the probability distribution of beta zn, and this is given by the recursion term over here, where we can see that it makes use of beta zn plus 1. Hence, it's termed as a backward recursion because we are moving this way for the computation of beta over here, in comparison to alpha, where alpha zn, we have to make use of the term of alpha zn minus 1. Hence, this is a forward recursion where we are moving from this direction, from left to right of the Markov chain. We'll now show a proof of the backward recursion expression over here. We start off from the definition of beta zn, which is what we saw earlier to be the conditional probability of xn plus 1 all the way to xn, conditioned upon zn. And we'll do a marginalization trick by introducing this random variable zn plus 1 into the conditional probability by marginalizing it away. And then we'll make use of the product rule to decouple this, or to factorize this into two different product terms over here. And we'll use the conditional independence, where we can see that in this case over here, once we have observed zn plus 1, which is this guy over here, we can pretty much see that all the other observed random variables of xn plus 1 all the way to x capital N becomes deseparated from zn over here. Hence, we can ignore zn and simply write this expression over here into this joint probability distribution. And then finally, we'll take one more step of conditional independence, where we can see that observing zn plus 1 over here, all the rest of the random variable of xn plus 2 all the way until xn becomes deseparated from xn plus 1, because this is going to block the path from the baseball from flowing from this direction to xn plus 1 and vice versa. And as a result, we can see that this final term over here becomes the beta term of zn plus 1, which then completes our proof that this expression here is can be used to compute the backward recursion of beta zn. Now, similar to the forward recursion, the beta term can also be computed using a backward recursion from the right hand side to the left hand side of the hidden Markov chain. Now, suppose that we are going to compute this term of beta Zn taking a state of 1, then what we are going to do here is that we are simply going to marginalize over Zn plus 1 and beta Zn plus 1 P of xn plus 1 condition upon Zn plus 1 multiplied by Zn plus 1 condition upon Zn taking a state of 1. And this summation term over here can be evaluated to the sum over k states of Zn plus 1, which we can write it into this expression over here of beta Zn plus 1 taking a state of 1 multiplied by xn plus 1 condition upon Zn plus 1 taking a state of 1 multiplied by Zn plus 1 taking a state of 1 condition upon Zn equals to 1 plus all the way until beta of Zn plus 1 equals to k multiplied by Pn plus 1 condition upon Zn plus 1 equals to the k state multiplied by Zn plus 1 equals to the k state condition upon Zn equals to the first state. And we can see that graphically this is equivalent to doing these operations on the trellis diagram. We are interested in computing beta of Zn taking a state of 1. So this would be equivalent to, in this case here, we have 3 states for Zn and Zn plus 1 respectively. So in this case here, it would be equivalent to taking beta Zn plus 1 equals to the first state, which is this guy over here, multiplied by Zn plus 1 equals to 1 and Zn equals to 1. This is equivalent to A11. So we are taking this product term over here. Notice that now we are moving from the right hand side to the left hand side of the trellis diagram, hence the term of backward recursion. So the next term that we are going to take as a multiplication would be the observation of xn plus 1 condition upon Zn plus 1 equals to 1. Hence this would be this term over here where we are going to observe this Zn plus 1 taking a state of 1 of this particular emission probability. We're going to multiply this term with this term and pass it over to beta Zn 1 over here. We'll see that since we have 3 states, we are going to have 3 different terms in the summation over here. So in the second term of the summation, we will have beta Zn taking state of 2 multiplied by the emission probability condition upon Zn plus 1 taking a state of 2 and multiplied by A12, and we'll pass it on to this beta Zn1 as well as the third term over here where we're going to multiply this term and A13, and we're going to sum everything up, and that would be equivalent to beta Zn. So we'll do this for all the other states where beta Zn is going to take a state of 2. We are going to compute this using the same sum product operation, and we are also going to compute this beta Zn taking a state of 3 using all the sum product terms as shown in this trellis diagram. Hence, as a result, the computational complexity of the backward recursion is also going to be k squared for a single step and k squared multiplied by n for the total backward recursion. So we'll now show proof that beta Zn, capital N, is actually equals to 1. Recall that we have gamma Zn equals to this conditional probability distribution here, which can be rewritten into this form using the Bayes rule, where alpha and beta is defined to be these 2 terms over here. So we'll marginalize over Zn on the products of alpha beta, where alpha beta term over here is essentially the joint probability distribution of x and Zn, since we have these 2 terms over here. And now we can see that in the case of n equals to capital N, which means that we have beta of Z capital N over here. In order for these 2 terms to be equivalent, we can see that it has to be the case where beta Zn must be equals to 1. This is simply because we can see that alpha Z of n is equivalent to the joint probability of x 1 all the way to xn, and Zn, if we marginalize away Zn, by looking at alpha Zn itself is already sufficient to define the joint probability distribution of all the observed random variable, and as a result, beta Zn needs to be set to 1, and we complete the proof here. Now, once we have evaluated the alpha and beta terms in the forward-backward algorithm, we'll now do an evaluation of the psi term over Zn minus 1 and Zn, which corresponds to the value of the conditional probability of Zn minus 1 Zn conditional upon x. And this consists of k by k entries. We will start off by from the evaluation of this expression over here, where psi Zn minus 1 Zn is equals to this joint probability distribution, and applying Bayes' rule, we'll get this term over here, where we will then apply conditional independence over Zn. So we'll see that once we condition upon Zn, this is equivalent to looking at xn, Zn, and then this pointing towards Zn plus 1, and we have Zn minus 1 over here. So xm minus 1 and xm plus 1. So we'll observe these terms over here. And then by observing Zn, we condition upon Zn here, we can see that all the other terms of xm minus 1, it becomes de-separated from xn, as well as all the other terms that follows xn plus 1 all the way to x capital of N. Hence, we can de-separate this into 3 terms conditioned upon Zn and Zn minus 1. And we can also see that conditioning it upon Zn, we can also de-separate Zn minus 1 over here, which means that Zn can be eliminated, and Zn plus 1, minus 1 can be also eliminated in these 2 terms over here. Then finally, we can see that this ends up to be the forward recursion term, which is alpha over here, which is actually the combination of this term and this term over here. So it will end up to be the joint probability distribution of x1 all the way to xn minus 1 as well as Zn minus 1, which is defined to be alpha Zn minus 1, and the beta term, which will correspond to this particular probability distribution over here. Now, finally, we can make use of this probability, the hidden Markov model, to do a predictive distribution. Given that we have observed the data to be x1 all the way to xn, we can actually use it to predict the next observation, the next possible observation of xm plus 1. For example, in financial forecasting, where we can actually make use of this expression over here. So I'll leave it to you to derive this following all the terms over here. But what's interesting here is that once we have derived this, we can see that all the terms here are actually known terms. So these are our emission probabilities that we have, as well as the transition probability. And the alpha term is used to compute the normalizing constant as well, and also this term here, which can be make use of to compute the this particular conditional probability or the predictive distribution of the next random variable.